Hello everyone, this is the first video of a series about multivariate calculus where I will explain some of the main and basic concepts about the subject. We will start by an introduction on which is the difference between single variable and multivariate calculus and having a brief recap on useful concepts like vector operations. Then we will see the del operator and which can be the operations on vector and scalar fields, such as gradient, divergence, and curl. We know that in single variate calculus, we have we analyze functions that go from R to R and that can be plotted in this way. When we move to multivariate calculus, we can have functions that can be from R to Rn, or from Rm to R, or further from Rm to Rn. The first ones can be plotted in this way, since from every point in an interval in R will be associated a point in Rn. In this example, we picked Rn to be free. So the 3D point that is the output of the function can be represented as a point in this curve. Then for functions that go from Rm to R, we can visualize them in this way, where we took m to be true. In this case, the input has to be a 2D point in this case, which will be a point in the xy plane, and the output is a scalar, so we take z, the third dimension, to be the output in this case. It's very difficult to visualize other situations because of the limitations of 3D space. Further on, we can have vector fields that can go from Rm to Rn, where every point in Rm is mapped to a point in Rn. To visualize this, we just took m and n to be free, so that every point in 3D space is mapped to a vector with 3 dimensions, as here. We will now see some of the vector operations. The first one that we're gonna analyze is the dot product. So given two vectors that can be A, made out of A1, A2, A3, and B, this B1, B2, B3, we have that the dot product is given by this formula, that is A dot product B is equal to A1, B1 plus A2, B2 plus A3, B3. We can see an example of this dot product or scalar or inner product, taking A to B 0, 3, minus 7, and B to B 2, 3, and 1. In this case, we have 0 times 2 being 0, then 3 times 3, 9, and minus 7 times 1, minus 7. So we have that A dot B is true. Now we're going to analyze the properties of the dot product. Firstly, it is distributive. So u dot v plus w is equal to u dot v plus u dot w. Then it is commutative, so v dot w is equal to w dot v. And then we know that if we take the inner product of a vector with himself, we have the norm squared of the vector. Then we have that with a constant c, this relation is valid, so we can multiply the constant c on any of the vector, like on v or w, and it is equivalent to multiplying both the inner product of them by the constant. Then we have that 0, like any vector dot 0 is equal to 0, and that if the inner product of a vector with itself is 0, then the vector is the 0 vector. We have an interesting theorem that on the inner product that says that the scalar product is equal to the magnitude of the first vector times the magnitude of the second vector times cosine of the angle in between. The angle is this one in this case. It can be extended also in 3 dimensions, but the drawing is in 2 dimensions. Now we're gonna move on in the cross product, which is defined only for 3-dimensional vectors. So taking A and B as showed, we know that vector product is given by this formula. This is a bit tricky to remember, but there is a simple tool that we can use, which is we know that the cross product can be given by finding the determinant of this matrix. The matrix is composed by having the first row. In the first row, the unit vectors of x, y, z. Then on the second row, we have the first vector, so the components a1, a2, a3. And then in the third row, the second vector. It is important to remember this because the cross product is not commutative. We can see that finding this determinant, we have the by cofactor expansion I that multiplies the determinant of this matrix and so on. This with a minus, so j that multiplies the determinant of this matrix and the k that multiplies this determinant. We know, of course, that the determinant of a 2x2 matrix is given in this way. And as an example, we take A to be 2, 1, minus 1, and B to be minus 3, 4, 1. Now, to compute A cross B, we can use even another trick to compute the determinant. So, instead of using the cofactor expansion, we will use the Cyrus rule, which is a trick that allows us to compute the determinant in a faster way by putting the first 2 columns of the matrix adjacent to the matrix, so that we can trace some diagonals. So we have this, this, and this diagonal, and this, and this diagonal. We see then that we can take the diagonals that go towards right with plus and diagonals that go towards left or minus. In this, I mean that we multiply each term of the diagonal, and if it's one of the purple ones, we put it as a plus, so this and this. And if it's one of the orange one, we put it with a minus. So in this case, we have as a minus j times 2 times 1, and I times minus 1 times 4, and k times 1 times minus 3. Well, eventually this would give us the result of 5 I cap plus j cap plus 11 k cap. We also have properties for the cross product, which are the opposite commutative property. So if we have u cross v, we will have that this is equivalent to minus v cross u. Then we have the distributive property, for which u cross v plus w is equal to u cross v plus u cross w. Then we have scalar multiplication that, as in the dot product, is interchangeable in a way, so we can multiply the scalar by each one of the 2 vector or by the cross product of u and v, and the result would be the same. And lastly, we have this property for which u dot product v cross w is equal to u cross product v dot product with w. Additionally, there's also a theorem for the cross product that is a geometric interpretation for which the magnitude of A cross B is equal to the magnitude of A times magnitude of B times the sine that is in between the two, of the angle in between the two vectors. We have to be careful that this only indicates the magnitude, because the direction of the vector can be found by right hand rule, for example. So pointing our index in the direction of A and our middle finger in the direction of B, of the right hand, then our thumb will point in the direction of the cross product of the two. Now we will analyze the del operator and show the operations that we can take on vector and scalar fields. We first look at what is a scalar and the vector field. So a vector field given the subset of Rn is a function f that goes from D to Rn. So every point x in the space is mapped to f of x that is in the space. So basically at every 3D point is associated a 3D vector. On the other hand, for a scalar field, we have that every point is associated with a scalar. So even if we have like a 2D point, for example, in the xy plane, it will be associated to a value f of x in R. So we plot it as a value in z, in the z-axis. The del operator is defined as such. So it is not a vector, it is an operator, but it's defined as I cap with derivative respect to x plus j cap with derivative respect to y, and k cap with the derivative respect to z, in 3 dimensions. The first operation that we are going to analyze is the gradient. The gradient of a scalar function f in x, y, z is defined as I cap that multiplies the derivative of f respect to x plus j cap that multiplies the derivative of f respect to y plus k cap that multiplies the derivative of f respect to z. In this example, we see that if we have our scalar function to be minus x squared and minus y squared, so being this surface, this paraboloid, then the gradient is given by the vector field minus 2x I cap minus 2y j cap. We see indeed that the gradient turns a scalar field into a vector field, where the direction of the gradient is that of the greatest increase of the function, while the magnitude of the gradient is the rate of the maximum increase. As we see, the direction of the gradient is towards the vertex of this paraboloid, while the magnitude we see that decreases as we get closer and closer to this, let's call it, vertex. The second operation that we're going to define is taking the divergence of a vector field. And this is defined as taking the del operator, the dot product with the vector field. We have, this is the del operator, the product with the vector field. We get the derivative of the first component of the function respect to x plus the derivative of the second component of the function respect to y plus the derivative of the third component of the function respect to x. And this is defined as the divergence of this vector field. The significance of the divergence is that this operation turns a vector field into a scalar field, and that the value of the divergence is the rate of the net mass flow of the function in or out at the point where the divergence is evaluated. This means that, for example, as an example, we have that in this point the divergence is negative because we see the flux is going inwards, while in this point the divergence is positive as we see the arrows going towards outside, and in this point the divergence is zero because the net flux is equal to zero. There are as many arrows going in as many arrows going out. Adding some numbers, we have that being, for example, f this vector field, the one that we saw before, then the divergence of this vector field is equal to minus 2, being the derivative respect to x of the first component of the function, and minus 2 being the derivative respect to y of the second component of the function, and this is equal to minus 4. We now analyze the curl of a vector field, which is being f three-dimensional vector field in Cartesian coordinates. The curl of f, so the cross product between the del operator and f, is defined as we saw in the previous slides as the determinant of this matrix, while p, q, and r are the components of big F. So this is equal, computing the determinant to this expression, that is the curl of this vector field. This formula doesn't tell us so much, but we can have a little insight of the significance of the curl. The curl turns in a vector field into another vector field, and the value of the curl of f measures the local rate of rotation of the function f at x. So the direction of the curl is the orientation via right-hand rule of the local rotation of f at x, while the magnitude is the rate of this local rotation. We see as an example, if we have this original vector field, that the curl of this has a direction upwards, since we see via right-hand rule that the direction of the rotation would be upwards, and that the magnitude is basically constant, since the rotation here is not changing. It's basically almost a constant rotation. Now we have some facts about the gradient, divergence, and the curl. So as the first one, we have that if f is a scalar valued function whose first and second derivatives exist and are continuous, this means that the function is of class C2, then if we take the curl of the gradient, this will always be 0. We can intuitively think of this as thinking as the gradient of a function as a field that points always in the direction of maximum increase of f. So it should not have any rotation, so it should not have any curl, because this would lead in a contradiction. Another theorem is that if f is a vector field of class C2 on its domain D, that is a subset of the 3D space, then the divergence of the curl is always 0. This can be proven applying the definitions of divergence and curl. We finished now the first video of this series, looking at some basic concepts of multivariate calculus, and in the next videos we will use these concepts on analyzing integrals that will be surface volumes or line integrals, and then in the end we will have some concepts about tensor calculus.